So now let's look at the construction of finite automata for non-finite languages, which means these are languages whose the number of elements in this language, right, is not finite, is not finite. It's not a finite number, right? So there could be infinitely many words in this language. That's what I mean. So let's look at some simple examples and also construct finite automata corresponding to them. Please remember that we will not be able to construct finite automata for all non-finite languages, right? For example, look at this language, right? This language is a non-finite language. We have seen this in the previous video, right? So language which is a power n, b power n such that n is greater than equal to 1. This is a non-finite language, but we cannot construct a finite automata which accepts this language. Or we cannot come up with a finite automata whose language is equal to this set. We cannot come up with it. Okay, that's the limitation of the finite automata itself, because finite automata has finite number of states. Okay? That's one of the fundamental problems. So given any non-finite language, we may not be able to construct a finite automata, but finite automata can certainly accept some non-finite languages or some infinite languages. Okay, so let's go through some examples so that it becomes clearer. Imagine if my language is all strings consisting of a and b, which means my alphabet itself is a comma b. So given this alphabet, I want my finite automata to accept all strings, including epsilon. Right? How do I construct this? Look at this. So my initial state has to be my final state also, because it has to accept epsilon, right? And it has to accept all the strings with a's and b's, right? So which means given a or b, I'll transition to the same thing. Because what is this language now? This language is nothing but sigma star, right? And we have seen this again in the previous video. We have seen these examples, right? See, look at this. This is a minimum finite automata because it has only one state which accepts sigma star. We saw this in the previous video, right? So what we are asking for in this case is all strings of a's and b's, which means my language is nothing but the clean closure of sigma, right? So this is your finite automata. So now let's look at second example. All strings of a's and b's excluding epsilon, right? So what is this language if you think about it? This is nothing but the positive closure of sigma. What is a positive closure of sigma? All the strings except AB, let's say AA, BA, all strings except epsilon. So I will not accept epsilon, right? Except that everything else should be there. How do you construct a finite automata for this? Look at this. So Q0, remember that this finite automata should not accept epsilon. Hence, this cannot be the final state. Now, given anything else, whether you give A or B, I will reach a state like this. And this is now my final state. Look at this. When I'm defining a finite automata, I'm defining all the transitions for all states and all possible inputs. Like even in this case. So for all the examples that we will learn of, the default assumption is that my alphabet is A comma B. Okay, let's stick to this fundamental assumption for all the examples that we'll see as part of this video. And we'll learn construction of finite automata from non-finite languages mainly through examples like this. And remember that I cannot construct this. I cannot construct a finite automata with just one state for this. I need at least two states, right? So this is your minimum finite automata to accept the positive closure of sigma. This is the minimum because I can't get away with just having one state. I need at least two states here. Simple examples, no rocket science here. Now let's look at another example. I want strings that start with A. Okay, just strings that start with A, right? It could be of any length. These strings could be of any length. They just have to start with A. So one way to think about them is you want A followed by X. Okay, this is what you want your language to be. Your language should consist of words like AX such that X belongs to sigma star. X is a word in sigma. Basically, that's what we are saying. X could be also an empty word, right? Or an empty string, right? X could be an empty string. All we want is basically that my string should start with A. How do we do this? Look at this. Okay. So, see, Q0 is not a final state because epsilon is not part of this language, right? Epsilon is not part of this language. So, Q0 will not be a final state. Now, if I start with A, If I start with A, I want to reach a stage. Obviously, this has to be the final stage because my language has A, right? AB, AA, all of them. It has to start with A. So single A also is part of this language, right? So this is my final state. Now, what if I get B as the first character or the first symbol? Then what should I do? If I get B as the first symbol, I should go to another state. The moment you have B as the first state, it can never be, because if B is your first character, right? So let's assume this is your Q2. Can Q2 be a final state? No, because if Q2 is a final state, we'll accept B also, which we should not accept, right? So once you reach this state, whether you get A or B, you'll continue to be in the same state, right? So this is sort of like your dead state. If you think about this, this is a dead state. This is a dead state because once you enter this state, which means you're starting off with B. So all strings or all words which start with B end up here. Now, once you start with B, whatever are the rest of the words, you'll continue to be stuck in this state, right? So number one. Number two, once you start with A, whatever exists afterwards, whether you get A or B, you'll continue to be in the final state. Look at this. For this state, I have transitions for A and B. For this state, I have transitions for A and B. For this state, I have transitions for A and B. That's it. So this is the finite automata which accepts all strings that start with A. Can you get away with less than 3 states? No. This is your minimum finite automata. You cannot get away with 2 states. Just try it. You'll fail, right? Again, we added states only when we needed them. We never added states unnecessarily when we were constructing the finite automata, right? Similarly, imagine if I want to build strings, okay? If I want a language that starts with AB, right? So which means your language is going to look like this. AB followed by X, such that X is element of sigma star, right? In other words, you want AB should be part of this language. You want ABA, you want ABB, anything after that. But you have to start with AB. So let's actually construct the finite automata for this. You start with Q0, you start with A. So this tells you that you're reaching a stage where you've read A, then you will read B. Okay, so this is cool now. So this has to be a final state now. So you read A, we're taking that information here, you read A and B, you reach this stage. Now, okay, 3 states. Can we get away with 3 states? Now what if, look at this, what if I read instead of AB at the beginning, if my whole word starts with B, I need a dead state then, right? If it starts with B, it should never reach the final state. Look at this, if I arrive at Q1 or if I'm at Q0 or at Q2, I can reach the final stage. But I want, if my word starts with B, I want to reach a state from which I can never come out. I should never be able to reach the final stage because I'm starting with B. And any word that is starting with B should not be accepted by this finite automata, right? So what I'll have here is I'll have a dead state here. I will have a dead state here, right? Now let's see. So from this state, AB is taken care of. From this state, look at this. From this state, if I get B, I go here. But if I get A, because AA should go here, right? Suppose if I have AB followed by anything else, I should stay in the final state, right? Once I reach a dead state, whatever I do, I have to be in the same dead state, right? So there's a very interesting idea here, which is if you're constructing minimum finite automata, in a minimum finite automata, so it's a very interesting property. In a minimum finite automata, there is at most, to be precise here, there is at most one dead state, because you don't need the second dead state. If you have only one dead state, all the cases that you want to get stuck in a dead state, you'll just point them or you'll just create transitions to that state. So whenever you're constructing a minimum finite automata where you want to have minimum number of states, there is at most one dead state. Of course, you could have 0 dead states also, right? This is a very interesting property about minimum finite automata and the number of dead states. Okay, so this is example 4. Let's look at a slightly more complex example. Strings that starts with ABA. Look at this. So here we saw strings that start with AB. Now we are slightly, step by step, we are complicating these examples, right? Again, this should be straightforward. From all the examples, see, the way we have chosen these examples is we're going from simpler problems to slightly more complex ones step by step, right? So I have A, so then I have B, then I have, okay, this is Q2, then I have A again. So this has to be a final state, okay, because my language, I want my language to be ABA followed by x such that x belongs to sigma star. This is what I want. Now, okay, so as is obvious, I need to have a dead state. Obviously, I need a dead state, which is Q4. Remember that Q4 is a dead state, because if my string or word starts with B, I should get stuck here. That should never be accepted. See, if I'm at Q0, Q1, Q2, any of these states, if I connect this B to any of these states, there is a possibility that I can reach the final stage. I should not even reach the final stage if I don't have ABA as my prefix for any string, right? So this is a dead state now. Since this is a dead state, anything that comes here should get stuck here. Very good. So your B comes here. Now after A, look at this. For this state, I have AB. For this state, I have B. For this state, A also will get stuck at dead in the dead state. Right? So this is my dead state. Right? For this, I have A, but I don't have B. My B will be here. Now once I have ABA as the prefix, anything else that comes after that, I'll be in the final state. Very simple way of constructing it. Right? So now let's look at a slightly different example. You want to construct, again, this is also a minimum finite automata. Remember, this is also a minimum finite automata. And as we discussed just a while ago, minimum finite automata only has one dead state, or at most one dead state. Okay. So now let's look at another example now. So suppose we want to construct a minimum finite automata that accepts strings that end with A, not start with A, but end with A. Okay. So very, very interesting example. So let's see. Okay. So these are languages like this, right? I have XA such that X belongs to sigma star, right? This is a way to think about it, right? So I have something for the end has to be A, right? Obviously epsilon will not be here. So Q0 is not a final state. Now, so what are all the words in this language? A is a word in this language because it ends and starts both with A. Similarly, BA is there, AA is there, all of them are there, right? The only thing is it has to end in A. So which means if I have A here, if I have just A, I should reach a final stage. First case, right? So this cannot be the final state. That's why I added one more state, because I want to construct the minimum finite automata. There is a reason why I added this state. Very good. Now look at this. Now after I get A, so this state basically says that the most recently read character or symbol is A. So if I keep reading A, I can stay here. But the moment I read B, I have to go back here, because my most recent word that I've read is B. So suppose imagine if I have this A, B, B. Okay, or simpler still, A, B. I start here, I get A, because my most recent word or most recent character is A, or most recent symbol is A, I'm here. But the moment I read B, I go back here. If this is the end of my word, then obviously this should not be accepted, right? So just using, so from here I have AB, from here I have A transition. Oh, from here what happens to B now? That's a good question. So what if I have a B from here? Okay, that's something that we have to worry about, because A is here, B transition is not there. So I'll just have a self transition here, because this state is stating that the most recent word that I've read, or the most recent, sorry, not word, the most recent character that I've read, if it is B, then I'll be in this state. The most recent character if I've read, if it is A, I'll be in this state. So you just need two states here. That's the minimum finite automata. No dead states here. So a minimum finite automata need not contain dead states, and hence I wrote here at most one dead state, which means you could have 0 dead states also, right? I hope these examples help you understand how to construct minimum finite automata and in general finite automata, the deterministic ones. So let's look at another example now. So in this example, we want to construct, again, I just put dots here to imply that we want to construct minimum finite automata that accepts strings that ends with BA. Okay, I just put dots there instead of writing the same thing again and again, right? But we want to construct a minimum finite automata. Now look at this. What will my language look like? It will be X followed by BA such that X belongs to sigma star, right? And what will that be? This language will have BA as an element, right? This language will have BA as one of the strings, right? It will also have ABA. It will also have BBA, because what are we saying here? We are saying it has to end in BA, right? And so on and so forth. So let's construct this, right? So I start with Q0. Remember, first let's construct for BA. Simple example, right? So I have B, this is my Q1, and this is my A, right? So this is my A, this is my Q2. Very good. So this has to be my final state, obviously. So this finite automata now accepts BA. Very good. Till now everything is good. but can I just get away with just 3 states? Because we want to construct minimum finite automata, right? So we'll not add a state unless it is necessary, right? So now let's see. So this says that I have, okay, so now from this, there is a transition to B, but there is no transition to A. What if I transition this to A to itself? So what does this say? If you keep seeing A at the very beginning, if you keep seeing A, just stay here. Don't worry about it. Just keep staying here, right? Similarly, if you have seen one B, and if you keep seeing B's, stay here. That's perfect. So for this state, transition with A, transition with B is defined. For this state, transition with A, transition with B is defined. Now we have one more state. Now look at this. I have seen BA, which is good. But now if I see B again, where should I go to? So what does this state tell us? This state tells us that the most recently read word is a B. Or the most recently read character, not a word, I'm sorry. The most recently read character is a B. So if I encounter, again, from here I have to, if I encounter a B, I should go back here. If I encounter an A, I can go back here. Look at things like this, right? What if I have BA, B, A? What if I have BA? Okay, so what if I have BA? Let's see. Okay, so BA, I reach here, but then again I encounter B, which means I go back here. Why did I go back here? Because if I encounter A, I can come back here. See, this BA this is also part of this language, right? On the other hand, if I have, let's say, BAA, okay, BA, now A goes back here. Now I have to start seeing, because I got 2 A's, I have to see B again here. Without seeing A, without seeing B, if I just see A, that will not be valid. So I go back to my state Q0, because from now onwards, I have to actually see both BA for me to have a valid word. Okay, again, we got away just with 3. Again, the way we think about it is, the way I construct it, very simple concept is, think about the simplest one. First construct for it, right? Whatever is the minimum finite automata that you required for this, for the simplest word or the shortest word that is part of your language. I constructed that. My initial state, my final state, everything is cool. Now I will try to keep adding these transitions so that for every state, every transition is defined without adding new states unless necessary. That's the rule that I try to adhere to, so as to get the minimum finite automata. Very simple concept. Again, the minimum states here is equal to 3. Let's look at another example, right? Let's look at this example. So this example states, again, I want to find a minimum automata which ends with AAB. So what is the language going to be? The language is going to be X AAB such that X belongs to sigma star, right? So this language will obviously contain AAB. This is the shortest word, right? It will also contain BAAB. It will contain AAAB, and so on and so forth. So first let's construct for AAB, the smallest word that is there in this language. Okay, so this is my Q0, right? So first I have A, my Q1, again A, Q2, right? Again B, okay, Q3. Okay, so AAB is now accepted. Very good. Now can I just get away with 4 states without adding another state? So what if I get B? Look at this. What if I get B first? If I get B, I'll stay in the same state, because after obtaining a B, I can still see AAB. So what if I have BAAB? Right? This is a valid word as part of this language. So if I get at the very outset, if I keep getting B's, I'll continue to stay here. So this state says that I've seen 1A. This state says I've seen 2 A's. This state says I've seen 2 A's followed by a B. That's the logic here. So after an A, if I see a B, I'll come back here. Obviously, makes a lot of logical sense. So for this state, A and B are defined. For this state, A and B are defined. What about this state? B is defined. If I see an A, where should I go back to? Look at this. If I see an A, this is very, very important. If I see an A, where should I go back to? Should I go back here or should I just stay here? Look at this. This is possible, right? A, B. This is possible. Look at this. A. If I just stay here, what does it mean? It means that I've seen 2 A's already. I've seen 2 consecutive A's. Okay, I might have seen more than 2 consecutive A's also. That's perfectly all right. Right? So the important aspect here is, if I connected this here, look at this. Instead of this connection, if I connected this like this, if I connected it like this, then would AAAB be part of my, would that be accepted by my automata? No, because A, B, it will not be accepted. But it should be accepted, right? Because it is ending in AAB, right? So I hope you got the concept on how we can construct these transitions using examples. Okay, so now for this also you have A and B. What about this? What about this? If you encounter an A now, so for example, again, we can easily solve this with examples. Okay, suppose if I have AAB, look at this. I've seen AAB. Now if I see an A again, where should I go back to? Look at this. If I've seen an A, what else do I need to see to accept this word? See, I've seen an A already, which means if I have AB, I'll accept this, which means from here, if my A, look at this, from here, if my A goes here, look at this. So I've seen AAB followed by A. Now if I just see AB, look at this, I've already seen this whole thing. If I just see AB now, this sentence, or sorry, this word ends in AAB. That's why my A transitions to this. Okay. Now what about B transition? What about B transition? Very important question, right? So what if I see AAB, B? Okay. Now I have to see AAB again. Look at this. I've seen AAB, which means I've reached here. Now with B, where should I go to? With B, I need to see the whole AAB again to reach the final stage, right? Which means my B should transition to this. Look at how we are using simple examples to construct this transition. And here, look at this. I have AAB as my substring. Look at this. I have AAB as my substring, or as my, not as a substring in this case, sorry. I have AAB as a suffix, right? Because I have AAB, which is how many characters are here? 3 characters. So I need 4 states here. If you notice, I have 4 states here. I have 4 states here. The initial state itself and the 3 states to cater to this 3 characters in the transition, A and B, right? So again, this is the smallest that you can construct. This is the minimum finite automata. This is the finite automata with the smallest number of states that you can construct. You can't do it with 3. I strongly recommend you try it with 3, right?